Hi everyone, Mrs. Hanson once again. It's a nice Sunday morning and I'm going to talk to you further in our chapter on qualifying acidity. So kind of picking up with our acid-base lessons of chapter 3 in organic chemistry. You know, the last time we were together, we were using a pKa chart to compare strengths of acids and bases, looking at a quantitative value, a number provided to us in a published chart. Here in our next section, 3.4, qualifying acidity, we begin to compare acids and bases by analyzing and comparing their structures, really without using the published chart of pKa values. We're really able to determine what side of an equilibrium would be favored, which one is going to be the stronger acids, just by comparing two structures and their ability to stabilize the negative charge. So let's begin really through just thinking through what stabilizes a negative charge. So to determine the relative strengths of two acids, and we're not being given a pKa value, we are able to compare the stability of their conjugate base and understand that the stronger the acid, the more stabilized its conjugate base becomes. So an important statement there. The conjugate base must be able to stabilize the lone pair of electrons that resulted from the loss of the proton. So to determine the stability of a conjugate base, we're actually looking at the stability of the lone pair. For example, let's say, for example, we have, just an acid such as acetic acid, CH3COOH. You hear that coo at the end. This is acetic acid. Its conjugate base, of course, is the loss of its proton, and you would see this then as O negative. We're going to ask ourselves, for the conjugate base, and I have to put all those dots in there, there's its conjugate base, how well is this negative charge stabilized by the structure? When I say the negative charge, remember that that's really a lone pair of electrons. In other words, remember when this, whatever this base was, when it reached out to abstract the proton, this shared pair of electrons in the covalent bond collapsed back onto the oxygen. The bond became a lone pair of electrons on the oxygen. How well does this resulting species, this conjugate base, stabilize that negative pair? We want the most stabilized structure so that this negative charge isn't being placed on an atom that can't handle it. So remember the strength of an acid. How easy is it to remove the proton? The easier it is, the more stabilized that negative charge is, the stronger the acid becomes. So that's what our game is here in this little section, is deciding, is this going to be a strong acid? And if so, it's because the resulting conjugate base does a fine job of stabilizing the negative charge. And in order to stabilize the negative charge, the conjugate base, we look at four main factors, right? So the effectiveness of a conjugate base's ability to stabilize its negative charge, that's the lone pair of electrons. Remember, just looking at that acetic acid example, what used to be a bond between the oxygen and hydrogen, if the proton is removed, this bond collapses and we form a lone pair. That lone pair creates a negative formal charge on the oxygen. How good of a job does that oxygen do at stabilizing the negative charge? So the more stable that lone pair of electrons becomes on the conjugate base, the stronger the original acid was. There are four major factors that influence the ability to stabilize the negative charge, and we're going to go through these one at a time. Notice the first says the type of atom that is carried on the charge. Here, the type of atom was an oxygen. So identify the element that's carrying the lone pair of electrons through the loss of a proton in a proton transfer. Is that negative charge going to be stabilized by resonance? Is there a high electron withdrawing group that will influence the ability to draw electron charge towards itself? Is there a highly electronegative element? That process we'll look at is called induction. And what type of orbital resides on the charge? Is it a tetrahedral 3-domain sp3? Is it a trigonal planar total of 3 domains? This is 4 domains, 3 domains. Trigonal planar sp2? Or is there just 2 domains in a linear molecule of an sp hybridized orbital? All 4 of those considerations help us determine the stability of the conjugate base. And from there, we're able to determine the strength of acids in comparison of one structure to another. We remember this order of factors as the term ARIO, A-R-I-O. What type of atom is on the negative charge? Is the negative charge, remember the negative charge is a pair of electrons. Is the pair of electrons being stabilized by resonance? Do we have a nearby electron withdrawing group producing the induction effect? And what type of orbital is that negative charge reside in? Is it a tetrahedral sp3, a trigonal planar sp2, or a linear sp hybridized orbital? As we go through each one of these examples, we begin to examine the structure of the actual conjugate base and its ability based on its molecular structure to stabilize negative charges. That's the topic of our 4th section, ARIO. The first letter in our little acronym ARIO stands for the term atom. What atom is carrying the negative charge? So in order to compare acidity of 2 compounds, let's take a straight chain carbon. Remember, this is a saturated hydrocarbon, and at the terminal end of the straight chain, we have a hydrogen. 4 carbons in a chain, we'll learn to call butane. Here we have 1, 2, 3 carbons in a row, and at the end, we have a hydroxyl group, the OH. We've learned to recognize this as an alcohol functional group. So what we're comparing is the hydrogen that's attached to an oxygen or the hydrogen that's attached to a carbon. To analyze the acidity of the terminal proton of butane, and remember there's, again, like protons, because we know every carbon must have 4 bonds. There are 1, 2, 3, 4, 5, 6 hydrogens that are equivalent hydrogens in that structure. We're just looking at one of the 6 possible hydrogens. Doesn't matter which of the 6 we look at, they're all equivalent hydrogens at the end of a carbon chain. When we look to see the removal of the proton, we draw what's known as their conjugate base. Remember that an acid and its conjugate base only differ by the presence or absence of the proton. When I remove the proton, remember removal of a proton causes a bond to collapse, we get a lone pair of electrons. This is now a carb anion. It has a set of lone pair electrons on that terminal carbon. Here we have an oxide ion. The lone pair that collapsed from the bond when the proton was abstracted now gets placed on the oxygen. So when we think about stability, we have to envision where that negative charge has landed. And to do so, just sketch out the conjugate base of the acids provided. And now you have a visual where we see the negative ion here is on the carbon. The extra lone pair electrons, the negative charge here, is on the oxygen. All right, so now we have an envisioned where the negative charge is, where the extra lone pair electrons have been placed. Which one is more stable? And so really we have 2 periodic trends to consider. When we want to determine whether oxygen or carbon will be a better atom at stabilization, ask yourself 2 questions, and it depends on if the periodic trend is in the same row or is the periodic trend in the same column. So number 1 says, when I want to look at 2 atoms, this is carbon versus oxygen. The larger the atom, the more stable a negative charge will become. That's the most important factor. The more electron shells there are, the larger, more polarizable electron cloud we have, it has a greater ability to stabilize the negative charge. However, if you think about the location of carbon and oxygen, they're the same period 2, straight across the row. Carbon and oxygen really are not that different in size. They have the same number of valence shells that's in period 2. They're both occupying their outermost electron energy in valence shell 2. So since they're in the same period, they're very similar sizes. So in that case, we defer to a second way of determining who stabilizes the electric charge, the negative charge, a little bit better than the other, and that goes by its electronegativity. The more electronegative atom will be better at stabilizing the negative charge. Now, just visually on our periodic table, we had mentioned that carbon and oxygen were in the same row. We said that that's period 2. So really the size is not the biggest influence because they're very similar in size. Because the size from the same row gives us the same number of energy levels, really the size difference is not significant. And so then we have to determine using electronegativity. Remember, fluorine is the most electronegative element. It has a published value of 4.0. But just ask yourself in that same row, who's closer to fluorine? And clearly you see oxygen is the more electronegative element. It is because it has more protons packed in its nucleus as compared to carbon, and therefore more protons will attract electrons more so than an atom with fewer protons. So between carbon and oxygen, oxygen is more electronegative. Therefore, you can go back to the original question, and in determining which one is the stronger acid, answering that says, well, the stronger acid is the one that stabilized the negative charge better as a conjugate base, and therefore the more acidic proton will be attached to the oxygen and not the carbon. Remember, I just wanted to emphasize, if the trend is comparing columns such as O versus S, who would better stabilize a proton? Such as this example. This is the same column, not the same row. These guys both live in group 6A on the periodic table. We want to pick the larger atom. It has a more polarizable, think of it as a squishier cloud, a larger electron cloud. This is N equal 3 in period 3 for sulfur, N equal 2, only 2 electron shells in the carbon atom. The larger orbitals outside of the nucleus are able to stabilize the charge. There's just a greater distance to do so. So since this is a larger electron cloud, a greater surface area to distribute the pair of electrons in will help to stabilize more so than a smaller atom, which has a smaller surface area to pack in some more electrons to try to stabilize the electron charge. So in the same row, the more electronegative element will be able to stabilize the negative charge better. In the same group, the same column, you want to pick the larger atom to help stabilize the electron charge. And so putting that together, ultimately we were asked which one was the stronger acid. Because the oxygen was more electronegative, it was able to stabilize the negative charge and therefore, when you think back to the original acid, this acid that proton on the alcohol functional group is a stronger acid than the butane, which did not do such a good job as stabilizing the negative charge. When I say stronger acid, which one of those two acids is more likely to give up its proton? So more likely to give up its proton. And in answering that question, it's more likely to be able to give up its proton because when that bond collapses and places a lone pair onto the oxygen can stabilize it. It's a more electronegative element, and it has more protons in its nucleus to help stabilize the extra electrons. So let's take a look at some practices I just pulled from your homework. We're going to compare two protons in this structure. And remember, we have a series of things to consider. The atom. Does it exhibit resonance? Resonance. Is there an inductive effect? And what about the orbital? But so far, I'm only said one of those four criteria, so that's going to be our focus. I'd like to do all four of those, and then at the end say, okay, let's consider everything we've learned and try some more practice. But one at a time, then we'll put it all together. So when I'm asking you to compare the two protons in this structure to find the more acidic proton, I'm really only asking you to consider one of the four criteria at this point. What about the atom? So here's our protons, kind of highlighted in red and highlighted in blue. The first, highlighted in red, is attached to a nitrogen. The next, highlighted in blue, is attached to an oxygen. Since these are in the same row, and that row is number 2, same period, size is not really an influence. Because they're in the same row, we have to go by electronegativity. Which one of these is best able to stabilize the negative charge is the more electronegative element. So who's closer to fluorine? Is it nitrogen or is it oxygen? So kind of thinking that through, you clearly see oxygen is the more electronegative element. And so here's kind of the out loud thinking. Visually, do you look at the conjugate base? When hydrogen is removed from the nitrogen, remember how this bond collapses and it forms a second lone pair on the nitrogen. This is the conjugate base of the red proton up above. Here, if this hydrogen is removed, the bond collapses and puts an extra pair of electrons on the oxygen. This is the conjugate base of the blue proton. Which one is doing a better job at stabilizing that negative charge? And we agreed that it would be the oxygen, the more electronegative charge. So even though they're in the same period, we see that the more acidic proton comes from the more electronegative element. This proton colored in blue was more acidic due to the fact that its conjugate base was able to stabilize the negative lone pair electrons better. Here's a couple more from homework. You're going to see quite a few of these, just trying to decide which one would be a better at donating its proton. To be a stronger acid, it's a good proton donor. And the answer is, which one is best able to stabilize the negative charge? The proton that's highlighted in red is attached to a carbon. The proton highlighted in blue is attached to an oxygen. Now these two atoms are in the same row. They're both found in period 2. So size really is not the influence here. So therefore, since it's in the same row, we have to go by electronegativity. Who is the more electronegative element between carbon and oxygen? And clearly you see oxygen as it's closer to fluorine. Because oxygen is more electronegative, it's able to stabilize the negative charge. think about what I've just said. This oxygen, when it loses a proton, has a better job at stabilizing the charge because it's a more electronegative element. Therefore, the blue proton is indeed more acidic. Here's an example where the proton is attached to a sulfur and the blue is attached to an oxygen. I'm going to write that above. Because remember now, oxygen and sulfur, well, they're both in the same group number, group 6A. And we know that as you go down the same column on the periodic table, atoms get bigger. So the bigger atoms are adding valence shells. So remember here we have sulfur in period 2, oxygen in period 2. So it's putting its electrons in the outermost energy level of the second shell. Since sulfur lives in period 3, it has 3 valence shells, which is a larger surface area, which means a greater surface area can distribute the negative charge better. You know, it has more area to distribute the negative charge, and therefore it will be able to stabilize that negative charge better. That means the red proton is more acidic than the blue proton. Sulfur's larger surface area distributes the negative charge, stabilizing it better than the smaller atom of oxygen. Let's try the next letter together, the R. ARIO stands for resonance, the letter R. The ability to stabilize a negative charge, which is that lone pair of electrons, really increases with the ability to spread it out across multiple bonds. So if you notice a proton adjacent to a pi bond, we have the ability to form resonance structures. And those resonance structures highly increase the stability because we can take that negative charge and distribute it through multiple places. So for example, in an ethanol, this is the functional group we are learning that is an alcohol. The proton, when it collapses, a hydrogen gets abstracted by some base and it collapses the bond. And so you have a negative bond here, a negative charge. You have this oxide anion, O negative. But here in acetic acid, when this proton gets abstracted and the oxygen this oxygen receives a pair of electrons when this hydrogen is removed, what that does is form a negative charge here. Now, they're both on the oxygen, so both pair of electrons, both negative charges, let's just draw that. Both negative charges are on the same atom. They're both on an oxygen. So the first ARIO, the atom, doesn't play a role here because it's the same atom. The atom that's got the negative charge is oxygen in both cases. So then I go down to the next letter, R. R stands for resonance. If the atom didn't help me determine which is the better acid, and the better acid is one that stabilizes its conjugate base, I go to R, which is resonance. Can this negative charge be resonance stabilized? Well, the answer in the alcohol is no. There's no pi bond in this particular molecule at all. These electrons are what we refer to as localized electrons. They have no ability to move through a process of resonance. However, the bond, when it collapsed on the carboxylic acid, carboxylic acid, can be delocalized. In other words, they can be resonance stabilized. The extra set of electrons can form a pi bond here. This pi bond would then come up onto the oxygen, and we form a resonance stabilized structure, where now the oxygen is carrying the negative charge up here. Remember, there were 2 dots. I didn't draw them in. And we could have a pi bond forming in that particular spot. That's a resonance stabilized structure. It can go back and forth and delocalize the pair of electrons. Delocalizing a pair of electrons increases stability. Resonance stabilized structures, increasing stability through the delocalization of the pair of electrons. So which one is more acidic? Well, this guy right here, because his lone pair of electrons will be resonance stabilized. And you can see the structure that we drew for resonance structure, we called the oxide anion from the alcohol, having very localized electrons. There is no resonance available, no pi bonding at all in that structure, versus the carboxylate anion that does exhibit delocalized electrons. Resonance structures are delocalized electrons, and therefore that produces a more stable conjugate base, and therefore acetic acid is a stronger acid than an alcohol such as ethanol. So in our ARIO, we look at the atom. If we can't make a judgment by the atom, we go to the next letter, R, resonance. Is any of the electrons, the pair that's forming from the abstraction of a proton, does that have any ability to be stabilized by resonance? And if so, that's the more stable structure, therefore its parent acid is stronger. For example, which proton is more acidic? The red proton or the blue proton? Notice the A for in ARIO, the atom, well, it's the same in both cases. So that's a non-factor. This proton is attached to an N. This proton is attached to an N. So the atom will not play a role in determining our answer. So we go to the next letter. That next letter is resonance. R, resonance. Does either of those lone pair electrons have the ability to be stabilized through resonance? And clearly you see a nearby pi bond in the blue proton. The resonance structure, if I were to abstract the proton in red, we would get a lone pair and a negative charge on the red proton. If this proton is abstracted, it's left, that bond collapses. I see two sets of dots and a formal charge of -1 now on that nitrogen. Well, these are localized electrons. There is no nearby pi bond to distribute the negative charge. However, if I redraw and I take off the hydrogen on the nitrogen that's this highlighted blue, now all of a sudden I have a negative charge on a nitrogen that has a pi bond nearby in just the right position. The adjacent carbon is involved in this carbonyl group, and that possesses a pi bond. Remember that vocabulary. Carbonyl is a C double bond O. That means we could have a resonance structure form where the set of electrons on the nitrogen that came from the original covalent bond here, that set of electrons can be delocalized, and we start structures that move that double bond around, forming, for example, that particular structure. I've moved the electrons from up here, and the oxygen is now carrying the negative charge, and the nitrogen developed no formal charge, 3 bonds and 1 lone pair. So this is what we refer to as a delocalized set of electrons. And here, notice that when we draw, sometimes I like to have my figures drawn as well, just in case my drawings end up a little sloppy. We get this first, we had called localized. We get the second conjugate base. The conjugate base for each of those protons is shown here. The proton was abstracted, the bond collapsed. The first nitrogen that was on the left side is called localized. The second hydrogen on the right when it's removed, forms a delocalized charge. The adjacent carbon has a pi bond. And that's the criteria then for making sure that resonance can occur. The delocalization occurs because this extra set of electrons can collapse, form a double bond. This double bond then forms another lone pair, and you've moved the negative charge all the way up to the oxygen. And that helps to stabilize. When you spread out the negative charge between bonds, you're stabilizing the negative charge. Remember, it's not one structure or the other structure. It's not flipping back and forth. It's a hybrid of both structures. So keep in mind, you could think of that as a dashed line, a delocalization of those electrons involved in that bond. The more acidic proton is the one that will be resonance stabilized. How about this one? In ARIO, the first question we ask ourselves is to consider the atom attached to the proton that will be removed. Well, it's the same atom in this case. They're both attached to carbons. All right, so the atom will not play a factor, so no influence here because it's the same. We go to the next letter in our ARIO acronym, and that's the term resonance. Are either of these resonance stabilized? So let's suppose I remove the first hydrogen, I'll say is colored in red. That puts an anion here. We still have this hydrogen, I didn't take it off. This is the conjugate base for the red hydrogen. Remember, there's a lone pair of electrons. This is now called a carb anion. Look to the left, look to the right. Is it attached to an atom that's involved in a pi bond? And the answer is no. Therefore, these are very localized electrons. They have no ability to be distributed across multiple bonds. Let's compare that to the blue hydrogen and draw its conjugate base. That hydrogen is still on, but now that hydrogen has had its proton removed, and therefore, I started to draw a little face. There's an extra pair of electrons and therefore a negative charge. It's still a carb anion. The lone pair of electrons, when the hydrogen was abstracted by some base, the base pulls off this hydrogen and that bond collapses, and there's the dots now that are on that carbon. So now, does this have the ability to stabilize its electron charge by distributing it through multiple bonds? And clearly you see adjacent is a carbon that's involved in a pi bond, and that's a good thing for resonance. That makes these delocalized. So the resonance structure that can set up, these electrons can move to form a double bond. These electrons can place the terminal carbon as the extra electrons. And so what happened? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There we go. The original double bond, right? So just follow the arrows. Here now is the double bond. Here now is the negative electron. So this is resonance stabilized. We are moving the double bond across a series of atoms. And remember, it's not one structure or the other. It's not flipping back and forth. It truly is a delocalized, where you can think of that being evenly distributed between all of the atoms there. And a further distribution of electron charge through multiple atoms helps to create stability. So this guy is the more acidic proton. How about this one? Well, look here. The red hydrogen is attached to a carbon. And remember our ARIO. The first criteria is the term atom. Well, I always consider that first. We go in order. And if atom doesn't help us, then we go to the next as well. Here, the hydrogen is attached to a carbon. Here, the hydrogen is attached to an oxygen. The atoms are different. They're in the same row, And so therefore, size is not going to be an influence. Size would dominate over electronegativity. So remember, if they're in the same column, we compare size. If they're in the same row, we compare electronegativity. Oxygen is more electronegative. It is going to be able to distribute the charge better on the oxygen to stabilize the charge. And so right now I'm already having a hunch that this blue hydrogen will be more acidic just because it's attached to the more electronegative oxygen as compared to carbon. Now notice this negative charge, when I form a conjugate base, I want you to notice that when I abstract that proton, this guy gets plucked off, this bond collapses, this has a negative charge, and I can see that it could be resonance stabilized. This guy here can be oops, I forgot this guy. Coming back here, we have OH. Here's that double bond O. When I think about what could happen in terms of resonance, this negative charge could absolutely be stabilized through resonance. This particular set of electrons can form a pi bond, forcing this to come up and make the oxygen carry the negative charge. And the double bond would be placed here. And when I abstract the proton that was blue up there, let's do that. 1, 2, 3, 4, up to an H. Here we have a carbonyl, and this hydrogen I'm leaving on, just so you can see that's the one I'm leaving on. And I'm going to focus on the blue colored hydrogen. When it abstracts, when it's gone, when it's taken, the extra lone pair of electrons that collapse get placed on that particular oxygen. And so, is this have the ability to be resonance stabilized? And the answer is yes, because the set of lone electrons can form a pi bond there, forcing this pi bond onto the oxygen. And so, that hydrogen's still there. The oxygen now has 2 dots here, and we have a double bond. This double bond that was present heading down in that carboxylic acid group now has a negative charge here. So both have the ability to be resonance stabilized, right? So both the blue, that's adjacent to a pi bond, and the red is adjacent to a pi bond there. So they both have the ability to form resonance. So what would be the dominating factor? And it's the first letter in that whole story problem is A. The atom itself is going to create a stable conjugate base. Because both exhibit resonance, resonance really wasn't the factor here. It was the first letter. The first letter stands for atom. An atom of oxygen is more electronegative than the atom of carbon, and therefore the proton attached to the oxygen is the more acidic proton. Let's move to the third letter in ARIO, and this is called induction. Induction is what's used to stabilize a formal negative charge by helping to spread it out. And let's compare the term induction from the term resonance. Induction is when we have an electron withdrawing atom or groups of atoms that inductively withdraw electrons from their surroundings. And I just think of this as based on polarity of the bond. In the polarity of the bond, we can see electron withdrawing groups, not delocalizing, not spreading out via pi bonds, but simply by an induction effect is based on the polarity of the bond. For example, here is a proton attached to an oxygen. Here is a proton attached to an oxygen. These A's stand for atoms, and that is not an influence because they're attached to the exact same atom, oxygen. The next letter is R. R stands for resonance. Well, aren't these both going to have the exact same ability to exhibit resonance? Because both oxygens are adjacent to the pi bond in the exact same position. So this means that there is no difference. They're the same. So the R cannot be used to determine the acidity. It's the same for both structures. The A, atom, cannot be used to determine more acidity because it's the same for both structures. But what about I, finally, the inductive effect? Do you notice on the carbon, there are very rich electrons around the chlorine. These are known as electron withdrawing groups. Based on polarity of the bond, you can see that the electron distribution is being pulled by a massive amount out towards the chlorine, which help to stabilize negative charge. The inductive effect, these highly polar bonds are pulling electron density away, electron density away from the oxygen that's trying to stabilize it. Let me say these polar bonds are pulling electron density about towards the chlorine, the more electronegative element. And that's a place where you want it to go because chlorine has a great ability to stabilize negative charge. So in other words, when I think about these charges, if oxygen here has a negative charge, it's going to be resonance stabilized, and it's going to be stabilized because the negative charge is also being pulled in this direction. So this oxygen has all kinds of help stabilizing that negative charge. It can do so through resonance, and it can do so through the ability of the inductive effect, where the chlorine helped to pull electron density towards itself, making this a more electron-rich area. Whereas the acetic acid with this boring little hydrogen tail here has no ability to stabilize negative charge. And therefore, because the A is the same for atom, R is the same for resonance, I look to see if there's an inductive effect. Are the highly electronegative elements present in the molecule, such as chlorine, to help stabilize negative charge? And that's certainly true with trichloroacetic acid. It is a more acidic proton than plain old acetic acid. When we have more than one electron withdrawing group, such as monochlorine, then dichlorine, then trichlorine, you can see an even greater inductive effect. So here, notice that acetic acid with 3 hydrogens here is a pretty strong acid, 4.75. But if I remove one hydrogen, the 3 that we started with, remove one hydrogen and add a chlorine, this becomes an even stronger acid. This proton is even easier to remove because this oxygen can stabilize the negative charge even better because of the inductive effect chlorine places on the electron polarity. All of the electrons are being pulled towards the more electronegative element, in addition to being pulled up as a resonance structure. And now look, 2 chlorines. When this oxygen is trying to stabilize its negative charge, it can do so not only through resonance, but it can do so in 2 different directions towards the chlorine. And the strongest acid here is the oxygen that can have not only resonance stabilization, but can kind of stabilize in 3 different directions onto those electronegative electron withdrawing groups known as chlorine. So look to see if there's any nearby interesting atoms that can help to stabilize through the process of induction. Here we have an idea of a little molecule where I have a carbon attached to an alcohol group. Here is a carbon attached to an alcohol group. This in red, this in blue. Which would be the more acidic proton? Well, ARIO, ARIO. They both are attached to the same atom. It's carbon, so that's a non-factor. Resonance. Well, there are no pi bonds here at all, so none of them are going to exhibit resonance. So A and R did not help me at all in determining the more acidic proton. So I'm left with the next letter, the inductive effect. Do you see any electron withdrawing groups near the proton? Well, I certainly do. See all these fluorines? Those fluorines have the ability to withdraw electrons. And when I say that, here's the electrons on the oxygen. These are leading out to carbons that have 3 fluorines on them. All kinds of electronegativity in that region of the molecule. So this negative charge on the oxygen can be stabilized by these electron withdrawing groups, fluorine, and I have a direction that's being pulled that these negative, very highly polar region on the fluorines can help to stabilize the negative charge on the oxide. Notice that it's not delocalized. These are localized electrons. This is not resonance. They're localized, but the distribution of charge can be brought into greater stability through the inductive effect, the ability of a polar bond to pull electron density towards itself, not move the bond, but help to stabilize the bond. And so clearly the red is more acidic than the blue. And you can see, just based on the structures we drew, the higher electron withdrawing groups of fluorine make the OH hydroxyl group more acidic when it's near more exciting atoms. How about this one? Find the most acidic proton. They're not color-coded, but I see only 2 protons that would be considered acidic protons here. And I realize that there are 2 hydrogens here. You know, those could be part of the game, but as soon as I go ARIO, there's 4 protons there that I can consider. The 2 that are attached to the carbon, I take off the plate right away, because here I have 2 attached to oxygen. Oxygen is more electronegative, so quickly I can say, all right, now I'm really deciding between these 2 hydrogens. Because oxygen is more electronegative, I can cancel out even worrying about the 2 hydrogens that are attached to the carbon in the center. So let's do ARIO. A, atom. Both of these that I have left, highlighted in red, are attached to oxygen. Okay, so that's not going to make my decision. I go to R, which is resonance. Both of these will exhibit resonance. The oxide here has a nearby pi bond that can help to delocalize. So this will be a delocalized electron pair. That's the same thing over here. These are carboxylic acid, COOH. Cool. This will also have a delocalized resonance structure. So that's really not a factor because it's the same for both. So that leaves us to I. The only next letter I is going to have to make our decision, the inductive effect. Which one is closer? Which oxygen is actually closer to the highly electronegative chlorines that would help to stabilize the next door electric charge? Well, here I can see that there's the carbonyl carbon, and then directly here, so that's 2 carbons away, are the chlorines. If I count here, here's 1, 2, 3 carbons away before I get to the chlorines. The greater effect will occur when it's closer, so therefore what I highlighted here would be more acidic. It is closer to the electron withdrawing groups on those on carbon 2. It's only 2 carbons away instead of 3 carbons away. The closer it is, the more the inductive effect has the ability to stabilize the negative charge. How about this one or this one? which is most acidic? ARIO. They're both attached to oxygen. So this hydrogen and this hydrogen are attached to an oxygen, so that's not a factor. Resonance. This hydrogen is attached to, it's right next door to the pi bond. These are both carboxylic acids. Cool, they're exactly the same functional group. So not a factor. Yes, they both have the ability to be stabilized by resonance. Not a factor. That leads us to go down to ARIO. Are any going to be, have a greater influence in terms of the inductive effect? Notice we have the same distance away. However, this only has one chlorine, where this has two chlorines, two groups of electron withdrawing groups. Two groups of chlorine tell me that it has twice the ability to stabilize the electric charge as compared to just one group of chlorine. Chlorine's not really a group. An atom would be a better word, wouldn't it? I caught myself. 2 atoms of chlorine versus 1 atom of chlorine. The more the better at stabilizing negative charge. So which is more acidic? Obviously the one with 2 chlorines to help stabilize the negative charge over a greater surface area. Easy enough. The letter O in ARIO stands for the type of orbital. So think about the ability of, the ability of stabilization of an electric charge and the distance it is to the nucleus to do so. The more stable the charge, the closer it is to the nucleus. Let's kind of just think that through what I'm trying to say. When I think of orbitals, I'm just thinking about the hybridization on the atom that's trying to stabilize the negative charge. Hybridization. We know that if it's sp3 hybridized, it's a tetrahedral molecular geometry. Tetrahedral. sp2 would be trigonal planar. It's attached to 3 atoms. sp means that it has 2 electron domains and that it's linear. When you think about tetrahedral, trigonal planar, and linear, think about it this way. When we have a straight chain carbon and all the carbons are attached to just hydrogens, kind of, all single bonds, this is what we refer to as an alkane, all single bonds. These all have sp3 hybridization. Alrighty, 4 bonds, tetrahedral molecular geometry, all single bonds. Compare that to an alkene. So I'm coming along here, and now all of a sudden, instead of all singles, I'm going to have a double bond, meaning that we've changed the molecular geometry just a little bit, saying that it's now trigonal planar. And this here now is what we referred to as sp2 hybridized in a double bond. And I know this could continue up and up and down. But an sp2 at the terminal end is now trigonal planar. This is what we referred to as an alkene. And finally, when we had a triple bond, this is what we refer to as sp in terms of linear molecular geometry, and this is what we refer to as alkynes. We have an alkane, alkene, alkyne. Now, the shorter the atomic orbital, the closer it is to the nucleus. Let's bring this into a better picture yet. Here's the single bond. See how long single bonds are? When we have a double bond, they're shorter. The electron density is pulling the atoms closer together, making a shorter bond. And when we have a triple bond, the bonds are very close together. I'm exaggerating, but we have long single bonds and we have very, very short, tight triple bonds, and the double lies in the middle, doesn't it? That the electron density is increasing with the triple bond between the 2 carbon atoms. That tells me that this hydrogen on the terminal end of an alkyne triple bond is very easily removed. Because the negative charge that would form on this negative charge here is very easily stabilized because it's very, very close to the nucleus of that carbon. Because of that triple bond pulling electron density so close to itself, it's closest to the nucleus, and that creates a more stable configuration. Compare that to a single bond, and if I were to draw the single bonds and draw, those long electrons, a shared pair of electrons, when I draw a lone pair of electrons on this carbon, the electrons are farther away from the nucleus, right? Because this is a very long distance, not really, but a longer distance than a triple bond. Therefore, this is less stable because it's further away from the carbon's nucleus. The shorter the bond, the tighter everything is. The electron density is being pulled really close to everything. So when this proton is abstracted and this bond collapses, these electrons get pulled all kinds of tight right there. When this bond collapses, these are very loosely held electrons. Therefore, this is a less stable configuration. So all of that to kind of talk through orbital. When you compare a triple bond, which we called an alkyne, the bond distance here between these two carbons is very short. That makes this hydrogen very easy to remove. I should maybe say very easy. I'll say easier. Easier to lose this proton because the negative charge is going to be stabilized. And so just think about that negative ion that forms is much more stable with this electron-rich area. It's closest to the nucleus. And that's where positive charges are, the nucleus, and therefore that creates stability. Compare over here, this is a carbon that's involved in a double bond. So remember, this would be sp hybridized. This is sp2 hybridized, meaning that a double bond in that particular ene, the alkene part of this molecule, when it forms its anion, is not as readily stabilized as it was over with the triple bond because there's a longer distance between the pi bonds here. That means that these electrons are a little further out from the nucleus and a little less stabilized than if it had electron-rich triple bonds. So the blue hydrogen is more acidic than the red hydrogen. And the same is true if you consider sp hybridization as well. So the most acidic comes from the triple bond. The next would come from a double bond, and the least acidic would come from a single bond. What type of orbital also affects the stability of a negative charge? The more S character in the orbital, the more stable the negative charge. What did I just say? sp3, right? sp3, that's 4 domains. That's what we would say is a tetrahedral, 4 domains. And that, of course, would be an alkane. Notice that the S is just 1/4 of all types of orbitals. 1 out of 4 orbitals, so 25% are an S character. What if I had sp2? Here's an S, p2. I could say that's p3, but I should have written maybe spp. spp is sp3. But now look. This would be 3 domains. It's trigonal planar. This would represent the alkene family, which is a double bond. There is 1 out of 3, 1s out of 3 total orbitals. 1/3 is 33% exhibiting S character. And of course, the alkyne is simply an sp orbital, right? sp is an alkyne. There's only 2 orbitals in a linear sp, right? This is the linear alkyne, 180 degrees. So 50% of the orbitals in a linear molecule are the s quality. So as the s character in the orbital increases, the more stable the negative charge. An alkyne is 50% s configuration. The other 50% comes from a p. It's the most stable conjugate base of the acids. When we compare the acidity of the compounds, the least acidic comes from the orbitals sp3, all single bonds. And next, we would have sp2, and the most acidic would come from sp, a linear molecule. The terminal end of an alkyne is much more acidic than the terminal end of an alkene, which is more acidic than the terminal hydrogen of an alkane, all with the ability to stabilize the negative charge based on the distance from the nucleus and the quality of the S character. Remember, we said this is 25% S. This would be 33.333% S character, and this is 50% S character. Of the 2 orbitals, half of them are S. Of the 3 orbitals, a third of them are S. Of the 4th orbital, sp3, of the 4 orbitals, a quarter of them are S. Increasing the S contribution to the orbitals increases the acidity. Which one is more acidic, the red or the blue? Well, I know, right? It's going to be easy. Here, this carbon has a double bond. It is sp2 hybridized. That means it has 3 domains. It's attached to 3 other atoms. sp2 hybridized. This carbon is attached to 4 other atoms. It's sp3 hybridized. It has 4 domains. It's attached to 4 other atoms. The one that exhibits the higher quality of S will have the proton that's more acidic. Double bond. A double bond hydrogen is more acidic than a single bond proton. These are that. I mean, that's really going to be this structure. When we say orbital, the highest comes from the triple bond. This is most acidic. The double bond, these 2 hydrogens, would be in second place, and the least acidic would be the hydrogens that are coming from sp3 hybridized carbons. So the most acidic to the least acidic, right? So sp is the most acidic, second place sp2, last place sp3. Structure 2. Here's a hydrogen coming off of the terminal end of that carbon. This is an sp orbital. Therefore, it is going to be more acidic than any of these sp3 hydrogens at the terminal end of those carbons. So all of those hydrogens that are there, but we don't see them, but we know they're there, all of those are equivalent hydrogens. All of them exhibit sp3. In the last terminal hydrogen of an sp, this would be the most acidic proton in that carbon structure. Notice here we have 9 equivalent hydrogens on this side, which are identical to the 9 equivalent hydrogens here. Those are all sp3 hybridized. Finally, here we have there's a hydrogen here and a hydrogen here. Notice that these are what we call equivalent hydrogens. They are both sp2. So there's 9 hydrogens that are equivalent in sp3. There are 2 hydrogens that are equivalent in sp2. So, of course, sp2 would be the more acidic proton, but it's exactly the same acidity as this particular proton would have. They're the same. Okay, hey, we've been working hard on ARIO, right? When assessing the acidity of protons, we generally use ARIO as the importance of stabilizing the effect. And I want you to go right down the order. Look at the type of atom. If no decision can be made, go to resonance. And if no decision can be made, look to see if there's an induction effect. And then finally consider the orbitals. What is the molecular geometry? Is it linear, trigonal planar, or tetrahedral? Based on those 4 types of things, we're able to figure out which structure is going to be the better acid. And that answer lies in which is better at stabilizing the negative charge. Now, in the little disclaimer down here, it says, this works most of the time, but it's not always 100% reliable. As with any set of rules, there's always rule breakers, these exceptions to the rule. I'm going to tell you the vast majority of these examples we will follow the ARIO, and I'm going to show you one exception that you should kind of just remember. So for instance, here we have ethanol, and we're going to consider polypropylene. Here's ethanol. It's an alcohol functional group. Here's the H. Here is the hydrogen on propylene. This particular carbon right here is attached really to 1, 2, other 3. There's 3 equivalent hydrogens there, keep in mind. And its pKa is 43. When we look at the conjugate base, we remove the proton and let the bond collapse, and we form a formal charge of oxygen and a formal charge on carbon. Clearly, we would predict, according to ARIO, that the oxygen, because it's more electronegative, would be better at stabilizing the charge, and that therefore this is the more acidic proton. And we'd be absolutely correct. The type of atom is consistent with this fact, even though this propylene, if I go down the list, ARIO, the first consideration is the atom. We were able to make a judgment right off the first criteria and say, wait, oxygen, more electronegative than carbon. Stop the bus right there and select the more electronegative element. If I chose to keep going and went to the R next, even though I made a decision, let's just say I'm oblivious to saying, oh, stop right there, I'm going to go down to R. This guy is resonance stabilized. Right? There is a resonance structure where the bond can form from these dots and this bond goes to form dots. There's a resonance structure. So I might be fooled into thinking, golly, since that has resonance, he might be more stable than the other structure, which has no resonance. But that's not the way the game works. I want you to go down in order. A, atom. If no decision can be made, then go to R, resonance. And then if no decision can be made, go to I. And finally, the last consideration is O, the orbitals. As soon as we were able to decide based on the atom, stop going down the list. ARIO is a guideline. It's a priority guideline, and it sometimes fails. And I say that just so rarely it does that I don't want you to be alarmed and thinking that, oh, why should I, kind of understand ARIO and use it if it's going to let me down frequently? And the answer is, well, it really won't. I promise, it really won't. There's just one common exception to ARIO, and if I show it to you, you'll go, okay, I'll remember that. This decision, here's an acetylene. This is the acidic proton of an sp hybridized carbon. It has a pKa of 25. Over here, we have an acid, ammonia, with a pKa of 38. Which one of those acids would be more stable? So here we have, just look at the conjugate base that forms. C triple bond C puts a negative charge on carbon. Here, the ammonia, NH3, well, this proton, again, there's no negative charge there. Nitrogen has no formal charge in that particular structure. The proton that was removed was attached to a carbon. The proton that's removed to force its conjugate base is attached to a nitrogen. So its conjugate base would place a negative charge on nitrogen. So this is the acid. This is its conjugate base. So if we have a negative charge on nitrogen and we have a negative charge on carbon, we would consider using ARIO, and rightly so, that the nitrogen, being the more electronegative element, should be the stronger acid. But it's not. If we had to judge the conjugate base stability, we would have concluded that the negative charge on nitrogen would be more stable, and therefore I would conclude that the ammonia must have been the stronger acid, but published pKa values verify that that's not true. It's just one exception. When I look at the terminal end of an alkyne, it's a pretty strong acid, more so than even the more electronegative element nitrogen. So just kind of remember this guy, even though it's attached to a carbon, is kind of a strong acid. Just kind of look for that and you'll be able to use. And also know you'll have a pKa chart. So when in doubt, just look up the pKa values. So there's always exception to any rule. This is just one exception I wanted to show you to where, you know, based on structure, I would predict the stronger acid to be the nitrogen because it's more electronegative, should be able to stabilize the charge better. But the actual answer is not, because this triple bond does an incredibly nice job of stabilizing a charge just because it's so close to the protons and the electron density here between the atoms is very rich. It can actually stabilize the negative charge a little bit better. When in doubt, check your pKa chart. I'm going to just keep practicing a little bit. If you're hanging with me, I'm doing some homework problems. It says, let's use ARIO to predict the more acidic proton. Well, here we have ARIO. Let's check the atom first. The acidic proton here is on an oxygen, so we would have oxygen stabilizing the negative charge. Hydrogen here is also attached to an oxygen, so it would have oxygen stabilizing the negative charge. It's the same atom. They're both oxygens, so this is no decision. How about R, resonance? This red proton will be a delocalized resonance structure because it has the carbon that's involved in a pi bond. So you can see when I have this conjugate pair form and this oxygen has its negative charge, I can see that I can distribute this negative charge and make this electron, you know, the extra negative charge, ultimately end up on that oxygen atom. So I have this drawn too far. That's why it looked bad. May I repair that quickly? Here is the oxygen. This is the negative charge, so that's where the double bond would form. That's why it looked upsetting to me, is I just had that drawn wrong. And so the resonance structure would end up looking like, and I know this goes on, it goes on up there, as a single bond, a negative charge, and the double bond here. And so that's resonance stabilized. So the red one is yes, it is resonance stabilized. And how about this blue? Does it exhibit resonance? And the actual answer is no, because the carbon nearby does not have a pi bond involved, and so there's no resonance. If I went on and saw inductive effect, the hydrogen exhibits inductive effect because I can see all types of chlorine here. The orbitals are really no factor. All right, no factor because they're all, I mean, I don't see double, triple bonds of carbons. So keep in mind, you're going in order. As soon as I found that the left molecule exhibits resonance, but the right molecule did not, I don't have to go any further. If I did go further, I noticed that the right blue proton does have influence by the inductive effect, whereas the left side, the red proton, has no inductive effect. So if I'm trying to decide between resonance and induction, go right down the acronym ARIO, resonance beats induction, and therefore the more acidic proton is the one in red. How about here? Which one is more acidic? Well, if you consider removing both protons and just look to see what conjugate base forms. We have the first conjugate base that looks like this, and the second conjugate base that would look like this, right? So, ARIO, the atom, make that your first decision. The red proton is attached to an oxygen, right? The blue proton is attached to a carbon. A is a very first decision. Can we make a decision right now? A, attached to oxygen or attached to carbon? Well, the answer is absolutely oxygen. I can automatically make my decision right here. That's the more acidic proton. And yes, I can see resonance involved. There is no induction. There is no orbitals to consider, but both have resonance. A beats R. How about another? Well, ARIO. This red hydrogen is attached to an oxygen. This blue hydrogen is attached to a nitrogen. Those are different atoms. So right off the bat, A is the atom. Oxygen is more electronegative than nitrogen. So I'm going to pick this one just based on the first criteria as being more acidic. Both exhibit resonance. There is no inductive effect. This is a non-consideration. So again, I'm just going between A and R. Both exhibit resonance. They're both, there is a pi bond in the adjacent carbon. So that is a delocalized set of electrons, but that's the same for both. And if I'm comparing which atom can stabilize an electric charge, you want to pick the more electronegative element, and that would be the oxygen. I'm going to see how long I've been talking. It's been 1 hour and 20. I'm going to stop the video here and pause, and then let you take a little break and come back.